Welcome everybody to Algebra 2, Section 9.1, Measures of Central Tendency and Variation. So Unit 9 is all about statistics and probability. And in Section 1, we're going to first define statistics. So there's going to be a lot of definitions here to start. In today's lessons in general, I should say. So statistics, numbers used to summarize and compare data. And then measures of central tendency. So these are numbers used to represent the center of data. And our three types of measures of central tendency are the mean, which is the mathematical average or the arithmetic average, and it's denoted by x bar is how we call it, x with a bar on top. And x bar, or the mean, is the first value, the second value, and really all the values, hence the dot 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 just keeps going until the final value, which will denote as n, for however many number of values there are, divided by however many things there are. So you add up everything you have, and then you divide by the number of things or entries or pieces of data or whatever. The median is the middle number when all the numbers are written in increasing order, aka least to greatest. And I want to note that sometimes if there are two middle numbers, you'll need to find the mean of those two middle numbers. So I'll say that's when necessary. The mode is the number that occurs most often. And it's possible that it could be more than one number. So let's say multiple numbers appear twice. Or it could even be none, if every number just appears once, for example. So, example 1. Below are the waiting times in minutes of several people at two different doctor's offices. Find the mean, median, and mode of each. So let's start with doctor's office A. So, it's already put in increasing order for us, thankfully. Our mean, or x bar, would be adding all of those numbers up and dividing by 9, because there are 9 different entries. When doing so, you would get 22. So that means the average waiting time is 22 minutes. The median waiting time is 20 minutes. That is the middle number of this data. And why those are different is because you have this number 32, which is bringing the 22 much higher, and the 30 is as well, bringing that number up. So in this case, most people, in this case 5 or more, waited 20 or less minutes, but those 4 that waited 24 or more minutes brought up our average waiting time. And then the mode, the number that occurs most often, is 24, because it occurs twice. So more people waited 24 minutes than any other time, though only 2 people waited 24 minutes. Doctor's office B, go and try this one on your own. This is also in increasing order. The mathematical average, or the mean, is 16. The median this time is 18. So that tells you that here this 8 and 11 really brought down the average down to 16, even though more people waited more than 16 minutes. The mode, number that appears most often here, is 18, because it appears 3 different times. Now we're going to talk about box and whisker plots. So we're going to talk about interquartile range with that, and a few other definitions. And interquartile range is going to be defined as quartile 3 minus quartile 1. That's what Q3 minus Q1 means, quartiles. Now, let's define what quartiles 1 and 3 even are. So quartile 1 is the median, once again, middle number when in increasing order, of the first half of data. So when the data is all laid out and you cut it in half, the first half, the middle number, would be the quartile 1. And quartile 3 is going to be the same idea. It's just going to be the median of the second half of data. So it's kind of like you're 1/4 through the data and you're 3/4 through the data, whereas the median would be halfway through. And our range is defined as the maximum number minus the minimum number. So for example, up here, since 20 was the median, our quartile 1 would be 18, our quartile 3 would be 24, and our range would have been our max minus our min of 18 minutes, meaning times can vary as much as 18 minutes. And here we see our box and whisker plot using all these points of data. So you have quartile 1, quartile 3 are the edges of the box. The median, the halfway point, or quartile 2 could be called, 2/4 halfway, is as a line through the box. And it won't always be centered on this box. You notice here it's slightly to the right compared to the rest of the box. And then the whiskers of the box and whisker plot go out toward the max and the minimum, where the plot ends. So this just kind of shows how the data spread out. So we're going to make a box and whisker plot here on example 2. So first, let's take this data and let's put it in increasing order. So you have 2, 2, 3, 3, 4, 5, 5. And by the way, it might be a good idea to cross out numbers as you use them. Maybe do so lightly, just in case you do make a mistake. Okay. 6, 7, 8, 8. Missed an 8. 9, 9. 14. Oh, sorry, I missed 12 there. 14. Oh, darn it, I missed 13 now. There we go. 14 and then 15. And now we need to define each of those things from before. So 15, that's the max. 2 is the minimum. The median is between 7 and 8, so it'd be 7.5 for the median. Quartile 3 would be at 9, and specifically that 9 because it's the second half of data, the median of that. So basically from here to the end, it's the middle number. And the first half of data, the quartile 1, would be 4. So now as we make our box and whisker plots, what you do is you draw your little number line. And the lowest number you see is 2. The highest number you see is 15. And so you can start at 2, or some people might even start at, let's say, 0, 1, 2, to kind of give a little bit outside the graph as well. And you just keep going, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'll go to 17. So I made mine, obviously, a little smushed together. You don't have to do that. You can have the numbers spread out as far as you'd like. You just want them at pretty regular intervals, so that way it's not like, let's say, 17's here and 18's all the way over here. because that misrepresents your data, which this is trying to represent how spread out it is. So now let's plot these different numbers. So the minimum is going to have a dot for the end of the whisker. The maximum is going to have a dot for the other end of the whisker. And our box starts at quartile 1 and ends at quartile 3. So it starts at 4 and ends at 9. And so we'll connect and make the box here. And then our median, 7.5, is where we draw a line through the box. And now we have our box and whisker plot. And we're also asked here to find the interquartile range. Oh, I'm sorry. I forgot to draw the actual whiskers there. So finding the interquartile range, or I'll abbreviate as IQR, is going to be done by taking the quartile 3, the upper quartile, and subtracting the lower quartile, aka quartile 1. So 9 minus 4 is 5. Now, we have to ask, is this data skewed or symmetrical? Symmetrical would mean basically from the median, or from the middle, or even just from the box here, that it's pretty even on each side. And we see there's an overwhelming amount of the whisker here compared to right here. So we would say, hey, the data is skewed. And how we can show that mathematically speaking, with just numbers, is looking at the interquartile range of 5 and saying, hey, that's where most of these numbers lie, is within 5 numbers of this. And we have numbers clear out here at 15. So that's 6 away. So it's pretty skewed over there. On example 3, now we're supposed to take this box and whisker plots and interpret what it means. So I want you to see if you can point out what the median is, the range is, the interquartile range, and then see if you think it's skewed or symmetrical. So the median is where this line is in the middle of the box, so 22. The range is the highest number minus the lowest number. 28 minus 16 is 12. And the interquartile range is quartile 3 minus quartile 1, the right side of the box minus the left side. So it's 26 minus 18, or 8. Now, is this data skewed or symmetrical? We can see it goes 2 out from the box, 2 out from the box, and our median is actually exactly halfway into our box. So the data here is not skewed, rather it is symmetric, or we can say symmetrical. Now, let's talk about shape, center, and spread. So, example 4, we're going to use these tables to make a line plot. So what is a line plot? Well, line plot, you would take these different babies here. We have 20 babies here that were a random sample, and we're going to put their birth month down. So every time you see a birth month, 5, you put a little X for that one. So we go to the second one, do 7, and just keep going through all the way until you finish the entire table, or both tables of all 20 babies. And so I'm just going in order and down. So it's not a bad idea to pause the video, go ahead and do this on your own. All right, so I've now made this line plot here. And so you can just kind of see, it's similar to a bar graph, just showing like, hey, how many were born in each month. You know, if you draw little bars on there, you can probably see that a little bit better. Now we're going to also do the birth weights. So 3.3 and so on and so forth. So go ahead and complete this one, and you can feel free to complete the mother's age as well. All right, so here's the birth weight, and then we'll go on to mother's age as well now. All right, and now it's asking, what do you notice about the mean and median for the symmetric distribution of baby weights as compared to the mean and median of the skewed distribution, which is mother's ages? So if you look here, the birth weight does look to be quite symmetrical. If you kind of draw a little curve on it too, you can kind of see how it goes higher in the middle, and it just decreases 4, 2, 1, 4, 2, 1. So very symmetrical. Where here, this ends up being up here, up here, up here. I should have drawn that a little bit shallower there. And goes down, it has to keep going before it ends all the way over here at 39. So once again, this is symmetrical. And this one is skewed. And we'll say, oddly enough, that this one is skewed right. And a lot of us might say, well, isn't it skewed left? Because most of the data is left. And we would say, well, what's happening is the reason it's skewed is because of this number all the way to the right side of the data. So it's pulling it farther and farther left. Whereas if that wasn't there, the data would end right here instead and look far less skewed than it does, even though it would still be skewed. And it asks us to compare the mean and median for these. So the mean for this birth weight, and you can find that, go and add those up and find the mean, be 3.5. The median, the middle number, and it can be easier to do this way by counting, would also be 3.5. And you can also find the mode, even though it didn't ask us to, which is also 3.5. Whereas here, the mean, median, and mode are 31.15 for an average age. The middle age is 30.5, and the mode are the most common of 29 and 30. So what do we notice about these things? And so we could say, hey, for the baby weights, the mean and median are the exact same because it's perfectly symmetrical. So there's not like a number pulling it higher or lower like we were talking about on the previous page. Whereas on the one that's skewed right for the mother's age, the mean and median are different because of that number of 39, that age 39 mother, skewing the data right, pulling it right and higher. So for each of the following, write which line plot's the best representative, or write neither. So if the median is more than the mode, which of these three represent that the best? Where the mean would be more than the mode. Actually, I should say just which of these two. So that would be the mother's age. Which one is the mean equal to the median? Well, that would be the birth weight. Well, which one is the mode equal to the mean? Well, that's really, so that was mode, once again, the most common number, and that would be the birth weight. And which one is the median less than the mean? And that would be the mother's age again. So you can see the differences between those different measures of tendency, measures of central tendency, I should say, when the data is skewed versus symmetrical. All right, on to our next page here. So now we're going to be talking about measures of variation, aka how dispersed the data is. So this describes the spread of the data. So the range we talked about earlier is the max minus the minimum, how far apart the values are. Variance will be defined as this symbol. That's going to be our variance symbol, that squared, and it's equal to the sum, that means sum, of everything that follows. In this case, it's going to be whatever x value is minus the mean. So any particular x value minus the mean, squaring that, and then dividing by the number of values there are. We'll walk through that in a moment. And the standard deviation, if you notice, it's this symbol without the square, meaning to get there, you would have taken the same thing, the sum of each x value minus the mean, square that, and divide by the number of pieces of data we have, the amount of the data we have, and square root the whole thing in order to get it from a square to no longer being squared. aka it's equal to whatever the variance was square rooted. And this tells you once again how far data is spread out. So now we have these wait times at the doctor's office, and we're going to find the standard deviation and range of these. So we said earlier the mean for this was 22. So now in order to find the variance, we said we took each individual x value and subtract the mean. So in this case, 14 minus the mean would be 8. Then we're going to square that. So 8 squared would be 64. For 17, you take 17 minus the mean, which will give you negative 5. Negative 5 squared is 25. So 18, you would take 18 minus the mean of 22, you get 4, negative 4. Negative 4 squared is 16, so you add 16, and you just keep going through the same thing for the rest of these numbers. So you'd end up having 9, 4, 4, 4, 64, and 100. And now we would divide that by how many different pieces of data we have, which is 9. And that ends up giving you that the variance is 32.2 repeating. So now we were asked to find the standard deviation. So the standard deviation, you square root, or I should write the symbol for standard deviation. You would square root that variance of 32.2 repeating, and you could just type square root and then hit up and enter that into your calculator there, which would approximately be 5.67. Now to find our range, this one's going to be quite a lot simpler. You just take your highest number minus lowest, 32 minus 14. The range is 18. So this tells us how far a standard deviation is from the mean, how far away on average the number is from the mean, and then the range. And let's now go to doctor's office B over here and do the same thing. So the numbers you would add together and then divide by 9, because there's 9 different wait times. In this case would be 64, 25, 16, 0, because it's 0 away from the mean. Once again, the mean here is 16 from earlier. 4, 4, 4, 16, and 49. So the variance would be 182, all of these numbers added together, divided by 9, which would be 20.2 repeating. Now the standard deviation would be the square root of 20.2 repeating, which is approximately 4.5. And the range is 23 minus 8, the highest minus lowest, aka 15. So now we found the standard deviation and the range. Now, why would this be helpful? What does this even mean? Are probably some of the questions you're asking. So let's talk about outlier. So an outlier is a value that lies outside most other values. That means that mathematically it is much smaller or bigger than most of those other values. And in order to be able to be defined as an outlier, we have to say it must be at least 3 standard deviations. Don't know why I capitalized standard. Standard deviations from the mean. So for example, on 2A, for the doctor's office A, you'd say the mean was 22, okay? Well, 3 standard deviations away would be 3 times 5.67. So if we were to have any outliers, they would be 22 minus 3.567. They would be smaller than that, or bigger than 22 plus 3 times our standard deviation of 5.67. So you take your mean and you subtract 3 times standard deviation and add 3 times standard deviation to figure out if any number is outside of those two, it would be considered an outlier and thus skewing the data because of it. It's important to note that in both of these cases, there are no outliers. Now, if you had a wait time of like 60 minutes for either of those, that would be an outlier, significantly different from the rest of the data. So in the following examples, we're going to start off with example 3. We're going to find the mean, median, mode, range, and the standard deviation. And we're going to determine if there's an outlier. So the mean, I'll trust you to find it, add up all the numbers, divide by how many there are, is going to be 17.8. The median, which you've probably seen me abbreviating as MED so far, is 10. It's the middle number of the data when it's in increasing order. The mode is 8. It's the most common one you see it twice. The range, the highest number minus the lowest number, in this case 82 minus 4, is 70. That's a big range. And then if you find the standard deviation, which once again would be finding the variance and square rooting, and remember how to find the variance was taking each individual value, subtracting it from the mean, squaring that, and then adding all of those values together, then dividing by the total number of values there are. Standard deviation here would be 21. Now, is there an outlier? So, how we figure out if there's an outlier or not, put outlier for our little notes of what we're doing. You would take the mean, once again, plus or minus 3 standard deviations. So here, in this case, we'll say, okay, we'll take 17.8 minus 3 times 21, the standard deviation, which would be 80.8. And we'll take 17.8 plus the same thing and end up getting negative 45.2. So then we say, okay, we ask ourselves this question. You don't have to write this down every time. We say, are there any numbers greater than the bigger one, 80.8? Oh, I should have noted that I flipped those around. I'm sorry. That it would be 80.8 is when you add to the standard deviation, add to the mean, and negative 45.2 is when you subtract. Sorry about that. You probably noticed that those were off. So are any numbers greater than 80.8 or less than negative 45.2? And so as we're asking this question, we say, oh, well, actually, yeah, right here. We say that, hey, 82 is. So we say, yes, there's an outlier, and 82 is that outlier. It exists far enough away from our mean. And we see here, 82, the next closest number to it is 22, and the rest of the numbers are fairly close, ranging from 22 to 4. I want you to try example 4 on your own. Alright, so here, the mean is 28.8. The median is 29.95. The mode there is no mode because no number appears multiple times. The range is 15.5. And the standard deviation is 5.01. So now, in order to find out if there's an outlier, you take the mean plus or minus 3 standard deviations away, and that would be 28 plus or minus 3 times 5.01. And this gives you the range of outcomes here for what it has to be to be an outlier. It has to be smaller than 13.77 or bigger than 43.83. So as long as between those or at those, it's not an outlier. So we say there's no outlier here. I misspelled outlier there. No outlier because no data is outside the range or is outside 13.77 to 43.83, or you could say is less than 13.77 or greater than 43.83. So if you have an outlier, how does it affect your standard deviation? We might notice between examples 3 and 4 that on 4, the standard deviation was 5.01. It was much smaller here, whereas on example 3, our standard deviation got much bigger here, especially compared to our mean of 17.8. Our standard deviation compared to that was quite huge at 21, whereas here, our standard deviation was much smaller than our mean. So if you have an outlier, the standard deviation, which I'll abbreviate as following, is going to be larger. And that's because the data is more spread out. So the farther spread out the data is, I should add A there to spread. The farther spread out the data is, the bigger the standard deviation. The less spread out, the smaller the standard deviation. So if you have an outlier, how does it affect the mean? Well, let's think. Back here, did 82 make the mean bigger or smaller? Well, it definitely made it much bigger, because if you add 82 and then divide, that's going to be much bigger than all of these numbers. So if you have an outlier, the mean in example 4, it increased, or I should say it increases for a large outlier. But we can have outliers that are small. So the mean, what would it do for a small outlier? Well, it would do the exact opposite. It would decrease. So a mean decreases for a small outlier because it would make the numbers appear much smaller than they actually are. In example 7, I want you to think about this for a second before just seeing what I end up writing. So if you have a data set that contains an outlier that's 4 standard deviations away from the mean, so pretty far from the mean, should you use mean or median as your measure of central tendency, aka like which one's going to be more reliable here? And you might have come up with a lot of different answers now after thinking about it for a moment. And I would say, that it would be the median would be more helpful here. And the reason why I say the median is I would look to example 3 as an perfect showcase of saying, hey, the mean was 17.8, But yet, most of the numbers here, if we exclude that outlier 82, end up being much closer to our median of 10 than our mean of 17.8. So it skews, if you have an outlier too, it skews the mean much more than it skews the median, because it moves the middle number by like 1 at most, whereas it moves the mean by quite a bit more. So I would say the median, and I would say my reason why is because it better represents the data, or you might even say the bulk of the data, where most of it's at. All right, that is all for section 9.1.